Okay, let's continue with the second part of the lecture. In the last example, we have gone through a rigid body which is subjected to angular acceleration of alpha and angular velocity of omega, and I have explained to you how we can represent this angular components or angular movements, either velocity or acceleration, in their respective vector form by using the right hand rules. Okay, and from there we calculate the velocity of A and the acceleration of A, the tangential acceleration, and also the normal components of the acceleration by using this relationship. Now we will further this by looking at a general motion, which is we can build our understanding from the rotation about a fixed axis. Yeah. So let's look at a general motion. This is where we left last time, and now we are going to move to a general motion. So in a general motion, we will have something like a general motion. This general motion can best explained by using a rigid body with 2 points. Let's say this is point A, this is point A, and this is point B. Okay, and from this we can easily draw the position vector, which is this is the position vector B relative to A. Now, if this rigid body has undergoing a rotation of omega, okay, and we represent that omega as omega AB, not omega relative to B, but omega AB. AB is the whole rigid body, and omega is the velocity or the angular velocity of omega AB. And let's, for the time being, take this as our coordinate system, x and y. And by knowing the relationship of this general motion, we can put the velocity of B relative to A as omega AB, yeah, cross position vector B relative to A. So that is the velocity of B relative to A. And if you want to find the velocity of A relative to B, you can use the same approach. There is no change of the angular velocity, still omega AB. Omega represents the whole body angular velocity, and then you have to cross with the position vector of A relative to B. Yeah, but we know that position vector A relative to B is equivalent to, but we know that position vector A relative to B is just the negative of position vector B relative to A, and then we can say that omega AB cross minus position vector B relative to A. And therefore we can say from this comparison of these two equations, we can say that B relative to A is equivalent to negative velocity of A relative to B. So this is the first relationship that I want you to understand, and this is also the relationship that we can deduce from this whole system. The next point is to find the angular acceleration, or the acceleration of B relative to A. And assuming that also at the same time we have the body of AB undergoing angular acceleration of alpha AB, and therefore we can find the acceleration of B relative to A. It has two components. Again, it's the same thing. There is this tangential component, and then there is this normal component. Yeah, and the tangential component is given by tangential. Only one, which is alpha AB cross position vector of B relative to A. And for the acceleration of B relative to A, the normal component is given by omega AB cross omega AB cross position vector B relative to A. And this is, we know this before, we can write this again as minus omega AB square with the direction of negative B relative to A. So this is the normal component. This is the tangential component. So from this relative motion, we can have three different components. The first one is the velocity of B relative to A, B relative to A, and then the other one is the acceleration of B relative to A. There is the tangential component, which is alpha AB cross vector position B relative to A, and there is the normal component, which is omega AB cross omega AB cross position vector B relative to A, and then we have this omega square AB position vector B relative to A. Okay, so that is the equations of a rigid body which is going through a rotation and at the same time having an angular acceleration. So these are all relative velocity. For us to find the absolute velocity, it will be quite easy, because if we know what is the velocity of A, then we can find the velocity, the fixed velocity, by knowing the one of the other components. We will do one example after this so that we understand what is going on. So let's do one example. Okay. So let's say this is example 2, yeah? It's example 2. Let's assume there is a rigid body. There is a rigid body, and there is a two position. This is A and this is B. Okay, and this rigid body is having an omega of 2 radian per second clockwise, and then we have acceleration, angular acceleration of, let's say, 5 radian per second square, and this is counterclockwise. Yeah. When it's almost a common misunderstanding among the students that omega AB is a property of a point, and they would like to find where is the specific omega. No, omega and alpha are the properties of the whole rigid body, whereas velocity and acceleration is a property of a particular point. Yeah. So when we say omega, there must be a body AB. When we say velocity, there must be a point V, B, or VA, or VO. Similarly, for angular acceleration, there is the angular acceleration of the whole body, alpha AB. You cannot say alpha A, which is point A, or alpha B for point B. So, and then let's say that the distance between A and B, okay, and let's say this distance is like 6 meters. All right, and we will do a coordinate system which is parallel to AB, and let's say this is X and this is Y. For the time being, we don't really care where the position vector, where the coordinate system is. We sort of use the easiest one for us to solve, and this is and perhaps the easiest one would for us to find X in the direction of AB. And therefore, from this system, we would know that position vector B relative to A, we can now easily say this is 6I. And therefore, then we need to write down what is the omega, the vector omega AB is 2 radian per second. It is clockwise, so it's in the negative direction, so minus 2k. By now, I hope the students are capable of writing down, and maybe I have to write down the unit here, radian per second, this is in meter. And then alpha AB, it is in 5k. I hope you know why is it positive 5k now, radian per second square. It's because it is, if you use your right hand rule, it is pointing upwards, yeah, so in the positive xyz direction. So what is the velocity of B relative to A? If we want to find the velocity of B relative to A, then we can find it is omega AB cross position vector B relative to A. So omega AB is minus 2k, cross position vector B relative to A is 6I, so k cross I is j, so 12j meter per second. Yeah, and then we can find the acceleration of B relative to A. There are two components, the tangential components and the normal component. And the tangential component is given by alpha cross R, alpha cross the position vector. So the alpha in this case, we know what alpha is. It's 5k. So it's 5k cross the position vector is 6i, and therefore the answer is 30j. Unit is meter per second square. And you can find the tangential, the normal component, position or the acceleration vector B relative to A in the normal component is given by minus omega square R. Minus omega is known as 2. The magnitude is 2. The position vector is minus I. So 6I. So 4 times 6 minus 24I meter per second square. Yeah. So there you go. You have your acceleration of this rigid body. And now we can combine the effect of these two components. Let's say we have two links and we want to find the velocity of everything. Okay, let's do this for a combined example. We'll stop now and do it the next time, in the next video.